a pleasure for me to introduce our next speaker, which is Blanka Horvath. You can start displaying your screen, please. And she's from Imperial College, and she will talk about data-driven market simulator for small data environment. So again, please, the screen is yours, please.
Thank you very much, Marco, and thank you very much for the organizers as well. It's a real pleasure to be here. I should say that just to please my colleagues from King's, I should correct this, that my correct affiliation is now King's College London. The Imperial was indeed the affiliation before. But yeah, but other than that, all is great. And yeah, I'm looking forward as well. Maybe a quick advertising beforehand. So if you have any questions regarding the talk, it is available in full detail on SSRN under this link if you type in the title of the talk. Right, and maybe another interesting thing to mention that there are further interesting applications of market generators. There is a risk article on all kinds of use cases of market generators, such as data anonymization, outlier detection, fighting overfitting. So there's quite a lot of things one can do with market generators, but we will get to that in a second. Yeah, so let me give the quick motivation. I'm very happy that Joseph was presenting already before me, because he did quite a lot of the work of defining things in a concise and very nice mathematical manner. So this is a perfect time to follow up on many of the concepts that he already presented. Also, here is another point to follow up on some work done by Joseph as well, because this work, maybe the original motivation for this work, when I started working with Hans Bühler and Ben Wood at JP Morgan, was a follow-up on their work with Joseph Teichmann and Lukas Gonon on the deep hedging. And maybe this also connects quite well to the last sentence of Stefan, because one of these quite peculiarities of machine learning models is, of course, the training data that you provide to them, and this is where market generators come in. So the observation was similar as the one that Stefan made earlier, and this originated now in the setting of the deep hedging. What happened there? Well, there was a hedging architecture, an architecture of the neural network, an objective function, and the training data provided was there a Heston model originally in the first instance of the work, and a Black-Scholes setup, and then the hedging engine was able to reproduce the hedging policies that we already know from the theoretical concepts. Now, if we want to use this on real data that we use for real life hedging purposes, then we better try to give this hedging engine some training data that is as close as possible to the scenarios of data that it will encounter in real life. And there comes then the motivation for market generators. Give the hedging engine as precise training data as possible, or to put it in a more neural network type of way, give it training data such that the network generalizes as well as possible in the case of later upcoming scenarios of market. So that is the work, and these are the co-authors, Hans Bühler and Ben Wood on the two ends of the screen were also involved in the deep hedging paper, and Terry Lyons, I do not have to introduce, who from whom the rough path theory basically originates, and Emmanuel Perez, who's a PhD student of Terry's and was also at JP Morgan at the time when I was there. So what is the big question here that we found maybe most difficult to answer and to quantify in this context? And what makes market generation for financial time series may be a little bit more difficult than generative modeling as it's known from other applications that I will get to in a second. It's very well summarized in this one image where we have on the left-hand side generation of returns, so generation of, let's say, distributions or empirical distributions for which we have very well-established metrics. We have the KL divergence, we have Wasserstein metric, so we have quite a few things to choose from to quantify if two distributions are close to one another or not. Now, this concept on the right-hand side for stochastic processes is not super easy or straightforward to generalize. If we want to say something about whether the blue paths or the orange paths are, or the blue process and the orange process are similar to one another, we could, for example, try to do that by checking in on certain number of marginals and then retreating back to what we have already known from generation of distributions. However, we will see that this is not sufficient. And on the right-hand side, what we have is a truly intrinsically infinite dimensional problem. And the generalization of this one-dimensional marginal case to this infinite dimensional setting is really not straightforward. And to come up with something that is a suitable way of addressing how two stochastic processes are similar to one another, or to be more precise, the stochastic process that we generate is a suitable reflection of the reality of the markets that we're trying to reproduce. This is not a simple question to answer. And I hope I will convince you that we come to a good conclusion on that. But on the other hand, this question is actually not new at all, because even in classical models or neoclassical models, as we could put it when we want to speak about rough volatility, or the Bergomi models, even there, one crucial aspect of modeling is that it should reflect several stylized facts of financial markets. It should reflect many properties of market paths that we observe. And this is exactly what we want to do in now this new deep neural network-based generative modeling approach as well, which, as I mentioned earlier, was already available in other AI applications. The good thing about it is that we can say that this is data-driven, as already in the presentation of Josef it was mentioned. So we make no a priori assumption of the distribution of the stochastic processes involved in there, as we would have done, let's say, in a Black-Scholes or a Heston case. So this is purely driven by data, but to say that this is non-parametric, this is maybe a little bit too much, too presumptuous to say, because of course, even if neural network is involved, there are many parameters of this neural network, from the input layer denoted by I to the output layer, and then there's quite a few choices of hyperparameters and parameters to make. But one can say, at the very least, that this neural network model is much more flexible than the models that we have known from a classical setting. And the reason for that is that the number of parameters for each and every classical model is a fixed number, while in the neural network case, we can add as many parameters as we want, and then the universal approximation theorem tells us that we can approximate distribution to a sufficient degree. So this is what lies behind. These are the two approaches that we would like to take a look at. And let me just make a very quick detour over here. So there could be something in between the two, because neoclassical models have their advantages and we have understood them very well. So there is a certain appeal to extend or augment existing models in different ways in order to gain more flexibility. without the backdraws of a full-blown generative modeling technique involved. One of them we have explored in the deep learning volatility paper, but I am conscious of the time, so I do not want to go into this too much. The background idea of here would be a mixture model between two models, let's say a Heston and a Bergomi, which is simple, but there's much more sophisticated versions of going so. So let's go into this generative modeling framework, and let's look into a little bit more detail of how this works. So as mentioned earlier, the baseline is an approximation or an approximation of a mapping. And here the mapping should be from one source distribution that we would like to map to a target distribution. And the target distribution is something that we observe in the data empirically. And what we learn is, in fact, this mapping from the original source distribution to the target distribution. And there are quite a few generative modeling techniques around that can be used for this and that do exactly this. There's a restricted Boltzmann machine approach, which is an interplay of two parts of a network. Then there's a very, very popular technique, the generative adversarial network, and several authors contributed on this front. So I would not be able to list everyone over here, but there's quite a few contributions and very nice articles on generative adversarial networks here. And then the approach that we take in this paper is by a variational autoencoder. And the reason for this is that we would like to focus on, as the title says, a small data environment. So we would like to be able to learn the distribution of a stochastic process of an observed time series when the available training samples from this time series are very scarce. We don't have much data available. We would like to be able to throw this into a generative network, in this case in a variational autoencoder, in order to produce more data of the same distribution sort as what was observed with respect to some objective function. So here the emphasis is really on the fact that the generative modeling technique works with very few data samples. And the reason behind, maybe this is a more intuitive explanation for that, but variational autoencoders resemble very much the idea of autoencoders, and autoencoders are a nonlinear generalization of a principal component analysis. So therefore, by design, they should work with few data samples. Okay, so these are the available techniques for generative modeling. But all of these, as mentioned earlier, are for one-by-one marginals at a time. All of them are flexible, all of them are data-driven, but they were all developed for static problems. And there's quite a few difficulties in adapting them to financial time series. One of them is obviously the fact itself that it should be adapted to a time series itself. And then there's other problems that it should be a financial time series, so it should reflect the properties of a typical financial time evolution of a financial path. And this is really not straightforward. We could, for example, mention the difficulties that financial time series are not stationary. So this will always be an issue, as it always has been earlier. Then the issue that we need to generalize this one marginal into an infinite dimensional setting is another difficulty. And then there's another difficulty of trying to make sure that it's not forward-looking, this modeling approach, but it's only incorporating the information from the past, which is addressed by Beatrice Acciaio and collaborators. But in this work, the approach we will take is via rough paths and signatures, and I'm very, very grateful for Joseph for making all this preparation for myself. Let me just go ahead. For some reason, this jumped back to the beginning. So I will get back to the point where I was. There I am. So yeah, let's get back to this picture where we started out. The return-based generation versus the path-based generation. This will be denoted by number 1 in the following algorithm that I will present to you, and the path-based generation will be denoted by number 2, which will refer to the signature-based approach. What we will also show in the algorithm is that we try to do the modeling as well in this path-based modeling technique, where we take several days returns at the same time and try to model the cross correlations of the days one after another. And what we will see is that the signature-based generation actually converges much faster with much less input data and much more precisely. So this is one of the results that we will observe in this presentation. So what is the general strategy here? As mentioned before, we want to do something where data is very scarce. So we start that with the S&P index, which gives us for the past 20 years a sample set of 5,000 data points. Then, as mentioned in the previous slide, we will be doing this pre-processing of the data in 2 ways. Number 1 was this return-based generation for daily, which is number 1, weekly and monthly returns. And on the right-hand side, we will do this in the pathwise manner by signatures. Or to be more precise, we will use log signatures for the reason that it's even more efficient regarding the training, and for the reason that log signature space is a linear space, and therefore outputs of the generator will remain in this space. But maybe this is too much detail, but this is for people who may have seen some of this kind of approach before. And then we will be using the lead lag transformation in order to account for business time. Again, a detail that might be interesting for people who have looked into this a bit more closely. Right, and then step 3 is the actual part when this generative model comes into play, where we're feeding in this pre-processed data into a generative model, in our case, into this variational autoencoder. And as I mentioned before, we want to account for the fact, as much as possible, that financial time series are non-stationary. So we would like to be able to condition on a certain number of market scenarios or market conditions. What we choose are the current level of the index, the instantaneous volatility at the starting point of the path segment that we're outputting or that we're modeling by the generative model. And the third one is something that actually incorporates information A and B. So number C is basically the signature of the previous path segment. And if we condition on that, this will also allow us to generate paths that are not only 1 week of length or 1 month of length, but by conditioning on one path segment, be able to create longer path segments up to a year or 2 years, or as we wish, by conditioning week by week or month by month on the previous path segment of the signatures. Then the fourth part is the post-processing step, because the output of the generator or of the variational autoencoder of this generative model is still in signature or log signature space. So we have to transform that back, and there's various ways to do that. In this paper, we propose one that definitely works, but there are also faster ones out by now. And then the last step is this question of the performance evaluation metric. So this last step I have in mind the GAN approach, where the generative network produces some output, and then there should be some kind of an evaluation of how realistic this this path is, or this set of paths is that the generative network has produced. And here we're back at the question of how do we evaluate good, or how do we create good performance evaluation metrics. And there's quite a few papers and outputs lately about what good performance evaluation metrics could be, and that acknowledge the fact that performance evaluation metrics for stochastic processes are actually not straightforward. Signatures answer this question quite well in a universal manner, because while other modeling approaches would be targeting, let's say, at stylized facts of financial markets, maybe picking out a couple of stylized facts that would be most important for this particular application, that would be a good approach to follow, maybe, but it's not really universal. So this would very strongly then depend on the application, and then from one application to the next, we might be producing grossly different market paths. But however, in this approach, if we use signatures, this is actually a quite universal approach for addressing this issue. So signatures provide a basis of functions on functional path space, and similarly to Fourier transforms, we can approximate curves as a linear combination of these basis functions, but signatures do so in an unparametrized way. They have the advantage as well that they're robust to missing data and to irregular sampling. So if we would like to model tick data, then this is also a good way of doing so. Background? No, not question. Okay. Signatures also provide this right framework for this performance evaluation metric. So a very nice paper from Ilya Chevirev and Harold Oberholzer. So again, this group in Oxford developed maximum mean discrepancy-based metric to generalize this idea of moment matching from marginals to the entire path space. And then I would like to mention also this paper by several authors, co-authors of Ni Hao and Terry Lyons, about the advantages of using lock signatures instead of signatures, with all the positive advantages listed above, but lower dimensionality. So I will quickly wrap up now, being mindful of the time. On the left-hand side, you see the output of a network. So this is step 3, and showing how the real paths, which are the blue ones, correspond to the input data, which is, the input data is the real paths, is the blue ones, and the generated paths are the ones from the variational autoencoder. And what you see on the left-hand side are different projections onto two-dimensional subspaces of this signature expansion. So you see that they all look quite similar, but again, this is all in signature space. Maybe one remark over here: the way we verified that the network works already quite well with as little as 250 samples was that we readed the entire experiment, this time with numerical data. With numerical data coming from a raw volatility model to be as close as possible to actual real market paths. So taking a model that is as realistic as possible, including all these effects of non-independence of increments and so on. So we took a raw volatility model and redid the entire study and experiment with that, but added that we were generating more and more original samples. So up to a couple of thousands or 10,000s of original sample paths of a rough volatility model. And the signature-based variational autoencoder framework was still as good as in the original case of as little as 250 samples. So that's the story. This is on the right-hand side, you see how it looks when we transform this signature-based output back into actual paths. And in the very end, I wanted to include this picture of how this conditional approach of conditioning on the previous path signature can be used to produce paths up to several years. So this is what this last image should demonstrate. And right, so with that, I thank you for your attention, and I just managed to do this well on time. So yeah, thank you very much. If there's any questions, I'm happy to answer.
So indeed, thank you very much, Blanka. Sorry for the wrong affiliation I gave to you before. And let's see if there are any. We have time. You are on time, so that's we have some space, some time for a question. Or then, if not, we will go to the virtual coffee break room where.
Yeah, then the questions can be asked there.
Yeah, but let's see if something appears. Maybe the chat is not updating. Or not.
Maybe I can ask a question if you want.
Of course.
Yes.
Thank you very much, Blanka, for the nice talk. Sorry, I missed a few slides because I had a technical problem. What is finally the core of the algorithm?
Well, I think there's two observations over here that were absolutely not clear when we started the work. So the core of the algorithm, if you want to put it this way, is a conditional variational autoencoder. The observation, which by now actually becoming or getting more traction, is to use signatures as a feature that we feed into the generative model. Through signatures.
Hello, Blanka. Sorry, may I interrupt you? Could you please, everybody else, mute their microphone? Only Blanka has it. And okay, please go ahead.
Okay, so that's one of the observations and one of the things that this work demonstrates, that using signatures is a much more powerful way of doing modeling, because market generation with as little as 250 or even 1,000 training data samples for this generative network is not enough. And if we go back to the very beginning of the motivation when we were speaking about deep hedging, or let's say applications that Yusuf were talking about, the original actual available data from markets is actually not enough, right? So providing the network, for example, this deep hedging network with tens of thousands of parameters, that wouldn't be enough to give it 250 samples of training data in order to get sufficient quality of a hedging engine. And therefore, it is quite important to generate or to create a network. Here it is, to create a generative network that can learn based on very little information due to this bottleneck structure, this autoencoder setting, and create more training samples of the same sort as the ones observed in the data. And the way we make sure of this is this maximum mean discrepancy type of metric on path space that was not available just a few years ago at all.
Okay, and in fact, what is the concrete meaning of using signature? Does it refer to a particular architecture, or?
Well, this is a part of the pre-processing and the post-processing step. So the architecture of the map is actually remains quite simple by that. If that answers the question, yeah. Okay.
Thank you very much, Blanka.
Thank you.
Okay, so I would say that I would thank both speakers for their nice talks, and I don't see appearing any other questions. So I think we could go to the coffee break room, and more questions will be there. Okay, great. Thank you all.